Alright, so I think I'm recording. Let's take a look at these polynomial functions and using the rational root theorem to, to help us in finding rational roots if they exist. So this rational root theorem or rational zero theorem, see, root is another word for zeros and also x-intercepts. We talked in class about this naming convention, that if you have a polynomial of nth degree, there's only 26 letters in the alphabet, and a nice way to name all the coefficients, since there may not simply be enough letters, is to just use the same letter and then an index and have that index be the same as the exponent. And in this rational zero theorem, we're interested in two numbers when it's written in standard form. We're interested in this leading coefficient, and we're interested in this constant term, and we actually are interested in the factors of the leading coefficient and the factors of the constant term, and we use the factors of the constant term to be the possible numerators and the factors of the leading coefficient to be the possible denominators, and we create a list of rational numbers that may or may not be zeros of the function. If the function has x-intercepts, and if those intercepts are rational numbers, then it will be in our list. But if that polynomial function has zeros that are irrational numbers, this doesn't provide a method, a way to find those. So let's look at these. We looked at some examples in class, and now here's some practice problems. The A naught is just the notation for the constant term. So for 6, we have factors plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So here for the leading coefficient, it's a prime number 2, so we have plus or minus 1 and plus or minus 2. So these values are going to be my possible numerators, and first I'm just going to use the denominator here of 1. So I'm going to get this list back, because the 1 divided by 1, 2 divided by 1, 3 divided by 1, 6 divided by, and of course I'm putting plus or minus in front of each of those. These are all the ones that have that denominator of 1. Now when I use the denominator of 2, I've got plus or minus 1/2. Now 2 divided by 2 is 1, and I've already got that in the list. So let's move on to 3. And 6 divided by 2 is 3, and I've got that in the list. So here's the list of possible zeros, and we'll just systematically go through there and try to look and see if we can find any of the x-intercepts, any of the zeros of this function. So I'm going to use synthetic division to do that. Now I could just plug in the values in the function and look for a 0. So since all of these are positive coefficients, plugging a positive 1 in is not going to ever equal 0, because you're just adding positive values together. So I'm going to try negative values in my synthetic division. So if I try a negative 1, I've got 2, 7, 6. If I get a remainder of 0, then I know I found one. And my remainder is not 0, so I know that the plus or minus 1 is not, because like I say, logic tells me that positive 1 is that these values are not going to add to 0. So let's come over and try negative 2. And this time I found one. Okay, so now that allows me to recognize that x plus 2, because see, if the intercept is negative 2 in factored form, that's x plus 2. So let's write down what we have now recognized. this original function, which is just a quadratic function, that using this rational zero theorem, we came up with a list of possible zeros, and then in searching that list, we found an actual zero at x equals 2. That allowed us, or excuse me, at x equals negative 2. That allowed us to factor this to x plus 2. And now from my synthetic division, this 2 and 3 is telling me that this is 2x plus 3. Okay, so now in factored form, if I set my equation equal to 0, ooh, if this is 0, then the zeros of this function, my x-intercepts, are negative 2 and negative 3/2. Now, let's look at the directions. It said to list all the possible zeros. We did that using the rational zero theorem. Then find the zeros by factoring and confirm they are in the list. Okay, well, I guess I didn't actually follow the directions directly. I factored it, just continued with my synthetic division. Suppose that we return back to our function. The synthetic division is nice when we don't have an x method, or this is a higher order polynomial. When it's a second order, when it's a second degree, then we have the factoring skills to look at this and say, okay, well, 2 is a prime number, so that I have 2x times x gets me 2x squared. I need two values that multiply together to give me 6. So if I try 2 and 3, well, if I have a 3, if I have a 3 here, hang on a second. All right, I'm back. What? Okay, so two values that give me 6. If I try 6 and 1 or 2 and 3 here, 2 times 2 is 4, 3 times 1 is 3, and 4 plus 3 is 7. So we're getting the same value. You know, in this case we now have two ways that we can come up with these x-intercepts. Since it was a quadratic function, we can use our factoring skills. But now that we know this rational zero theorem in combination with synthetic division, and also sometimes we'll have to factor, we can come up with the zeros if they're rational zeros. Well, the same over here. We typically don't try to factor over irrational numbers. We just jump in and use the quadratic formula. So, hope that helps. I'll do the next one in another video.